The destroyer HMS Zubian commissions on June 2, 1918, at Malta. The ship measures 269 feet length, 27 feet beam, and displaces 1,250 tons. The specifications are unremarkable for Admiralty M-class destroyer. What is remarkable is that Zubian did not exist 1 month earlier. The ship is assembled from salvaged sections of 2 destroyers, damaged beyond conventional repair. HMS Zulu, mined on November 8, 1916, losing stern section. And HMS Nubian, torpedoed on October 26, 1916, losing bow section. Engineers at Malta Dockyard spliced the undamaged bow section of Nubian to the undamaged stern section of Zulu, creating hybrid destroyer named by combining source ships' names. The repair philosophy, driven by wartime necessity and shortage of destroyers in Mediterranean, demonstrates that naval vessels can be reconstructed from salvaged components when conventional shipbuilding cannot provide replacements quickly enough. The concept, pioneered by HMS Zubian in World War I, influences World War II repair doctrine, where damaged ships are often rebuilt using components from other damaged ships rather than being written off as total losses. The most extreme World War II example is USS Porcupine, submarine so severely damaged that conventional repair is impossible, converted instead to floating, non-self-propelled parts depot, providing components to operational submarines throughout Pacific War. HMS Zulu's damage occurs on November 8, 1916, when ship strikes mine off Dover while conducting patrol operations. The mine detonates beneath stern, destroying propeller shafts, rudder, engine room, and everything aft of midships. The forward section, though damaged by shock and flooding, remains structurally sound. The ship is towed to port and assessed for repair. Conventional repair would require building new stern section, installing new propulsion machinery, and conducting extensive structural work. The time required exceeds 6 months, and cost approaches building new destroyer. The Admiralty determines Zulu is total constructive loss and removes ship from active list. But forward section is preserved rather than scrapped, stored at Malta Dockyard, pending possible use. HMS Nubian's damage occurs on October 26, 1916, when ship is torpedoed by German submarine in English Channel. The torpedo strikes bow, destroying forward section to approximate midships point. The stern section, though shocked and damaged, remains structurally intact, with machinery functional. The ship is towed to port and assessed. Again, conventional repair is not economical. Building new bow section and repairing structural damage would take months and cost nearly as much as new construction. Nubian is declared constructive total loss, but stern section is preserved, towed to Malta, and placed in dockyard storage near Zulu's bow section. The creative solution emerges when Malta dockyard constructor Charles Lillicrap examines both hulk sections and recognizes that Zulu's intact bow could mate with Nubian's intact stern. The concept is unprecedented in Royal Navy practice. Ships are built as complete units, or repaired by replacing damaged sections with newly built components. But combining sections from different ships has not been attempted. Lillicrap proposes that Zulu's bow and Nubian's stern are compatible enough that joining them will create functional destroyer at fraction of cost and time required for conventional construction. The technical challenges are substantial. The hull sections come from the same class, but were built in different shipyards to slightly varying specifications. The join point must align structurally, allowing welding or riveting strong enough to withstand sea conditions and combat stresses. The systems, electrical, hydraulic, steam, must be connected across join with minimal modification. The weight distribution must allow proper trim and stability. The engineering analysis determines join is feasible but requires precise alignment and extensive structural work at mating surfaces. The construction begins in April 1918. The 2 hull sections are positioned in dry dock with join point carefully aligned. The alignment requires adjusting one section's height and orientation to match other section within millimeters. Once aligned, temporary supports hold sections in position while permanent structural members are installed. The joining uses combination of riveting and welding, creating structural connection as strong as original construction. The process requires approximately 6 weeks for structural joining, plus additional 4 weeks for systems integration and testing. The systems integration proves complex. The electrical systems from Zulu and Nubian use compatible components, but different routing and junction box locations. Electricians must connect forward and after electrical networks, ensuring all circuits function correctly. The steam lines from Nubian's boiler rooms must connect to Zulu's forward heating and auxiliary systems. The fuel oil system, water system, and compressed air system must be integrated. The work is tedious, requiring custom fabrication of hundreds of fittings and adapters. The completed ship undergoes sea trials in late May 1918. The trials validate that structural joining is sound and systems function correctly. The handling characteristics are normal for M-class destroyer. The maximum speed of 34 knots matches original specifications. The endurance and seakeeping are adequate. The ship is commissioned as HMS Zubian on June 2nd and enters service with Mediterranean Fleet. The operational career is brief. Zubian serves from June through November 1918, conducting patrol and escort duties in Mediterranean. The service is uneventful. No combat actions. No mechanical failures related to hybrid construction. The ship performs comparably to conventionally built destroyers. The armistice on November 11th ends combat operations. Zubian continues serving in peacetime Mediterranean Fleet through early 1920s before being placed in reserve. The ship is sold for scrap in 1928, having served 10 years, including construction period. The legacy is establishing precedent that damaged ships can be rebuilt using components from other damaged ships. The concept, validated by Zubian's successful service, influences repair doctrine in World War II, when ship losses exceed production capacity and damaged hulls represent valuable resources. The most extreme application is USS Porcupine. Submarine damaged so severely that hull itself cannot be repaired, but machinery and equipment can be salvaged for use on other submarines. USS Porcupine, SS-176, is Salmon-class submarine, commissioned in August 1936. The submarine displaces 1,449 tons surfaced, measures 298 feet length, and mounts 8 21-inch torpedo tubes. The design represents late 1930s American submarine development, incorporating lessons from earlier classes while preceding World War II designs like Gato and Balau. Porcupine conducts 5 war patrols between December 1941 and May 1942. Operating from Pearl Harbor against Japanese ships, the damage occurs on June 29, 1942, when Porcupine is conducting submerged approach on Japanese convoy off Kiska in Aleutian Islands. Japanese depth charge attack forces Porcupine deep, at approximately 500 feet beyond design depth. Hull begins experiencing structural failure. Multiple hull fittings rupture. Flooding begins in multiple compartments. The crew conducts emergency blow, forcing submarine to surface despite continued depth charge attacks. The submarine surfaces out of control, broaching its steep angle. Japanese escort vessels immediately engage with gunfire. Porcupine's crew abandons ship under fire. Japanese forces cease fire, allowing abandonment. 47 crew members are rescued by American forces. 7 are lost. The abandoned Porcupine remains afloat, but severely damaged. American forces recover the drifting hull and tow it to Dutch Harbor, Alaska. Assessment reveals catastrophic damage. The pressure hull has multiple fractures from exceeding depth limits. The main ballast tanks are ruptured. The propeller shafts are bent. The control surfaces are damaged. The electrical systems are flooded. Conventional repair would require rebuilding most of submarine at cost exceeding new construction. But the machinery, torpedoes, weapon systems, electronics, and equipment, though water damaged, can be refurbished. The submarine is towed to Mare Island Naval Shipyard in California for evaluation. Mare Island engineers determine that Porcupine cannot be economically repaired to operational status, but contains valuable components. The decision is made to convert submarine to floating parts depot, designated 964. The conversion involves removing all salvageable equipment, cataloging components, and organizing submarine as floating warehouse. The pressure hull, though unsuitable for diving, provides protected storage space. The compartments are dried out, cleaned, and fitted with shelving and storage racks. Components from Porcupine's machinery are refurbished and stored. Additional spare parts for other submarines are loaded, using Porcupine's compartments as organized storage facility. The concept expands beyond original plan. Porcupine becomes not just storage facility, but mobile repair station. Workshops are established in compartments, allowing on-site refurbishment of components. Specialized equipment, including lathes, welding gear, and electrical test equipment is installed. Technicians are assigned to operate workshops, refurbishing components, and fabricating custom parts for submarines requiring repairs. The floating depot provides services at forward bases where permanent repair facilities do not exist. The deployment in Pacific begins in 1943, when Porcupine is towed to forward base at Midway. The submarine, no longer self-propelled, is positioned at dockside, providing parts and repair services to operational submarines. The services include supplying replacement motors, pumps, valves, electrical components, torpedoes, and specialized items not available from standard supply system. The workshops fabricate custom parts when standard items are unavailable. The capability significantly reduces time submarines spend in rear area shipyards, allowing faster turnaround between patrols. The value is demonstrated repeatedly through war. Submarines completing patrols with equipment casualties can obtain replacement components from Porcupine immediately, rather than waiting weeks for parts shipment from United States. The immediate availability keeps submarines operational that would otherwise be sidelined pending parts. The mobile repair capability allows conducting repairs that would normally require shipyard facilities. The cumulative effect is increased operational availability for submarine force in forward areas. The movement through Pacific follows combat advances. Porcupine is towed from Midway to Pearl Harbor, then to Guam, then the Subic Bay in Philippines. At each location, the floating depot supports submarine operations. The towing operations are complex, requiring ocean-going tugs and favorable weather. But once positioned, Porcupine provides stable platform for supply and maintenance operations. The conversion from failed submarine to successful support ship demonstrates that vessels unable to perform original missions can provide value in alternative roles. The crew assigned to Porcupine numbers approximately 40, consisting of supply personnel, technicians, and administrative staff. The living conditions are better than operational submarine, because vessel remains at dock rather than going to sea. The work is tedious rather than dangerous, involving inventory management and component refurbishment rather than combat. But crew members take pride in supporting operational submarines, knowing their work directly contributes to patrol success. Chief Machinist Mate Walter Hayes, serving on Porcupine from 1943 to 1945, describes the mission. "We kept submarines running. When sub came in needing motor or pump or any component, we provided it immediately. We saved submarines weeks in shipyard. We fabricated parts that didn't exist in supply system. The work was unglamorous but essential. Operational submarines depended on us. We took pride in never saying we couldn't provide something or make something needed." The comparison to other non-traditional ship conversions shows Porcupine represents extreme example of adaptive reuse. Multiple ships during war are converted from original purpose to different roles. Destroyers become troop transports. Cruisers become mine layers. But Porcupine's conversion from operational submarine to non-propelled floating warehouse is more radical transformation. The ship no longer performs any function resembling original purpose. The value is entirely in salvaged components and holds use as floating structure rather than diving vessel. The post-war disposition occurs in 1946, when Porcupine is towed to Mare Island and decommissioned. The remaining equipment is removed. The hull is evaluated for preservation, but determined unsuitable. The submarine is sold for scrap in 1947. No preservation effort is made. The ship's service, while valuable during war, is not dramatic enough to generate preservation advocacy. The hull, extensively modified and damaged, lacks historical integrity worth preserving. The legacy is reinforcing principle that damaged ships retain value as part sources and support vessels. The concept, pioneered by HMS Zubian, combining two destroyers into one, extends in World War II to converting irreparable submarines into floating depots. The modern equivalent is cannibalization, removing components from damaged aircraft or vehicles to repair operational units. The practice is standard in military logistics, but Porcupine represents formalized implementation, where entire vessel becomes dedicated parts source. The engineering lessons include recognition that ships are collections of components that can be reconfigured rather than indivisible units. Zubian demonstrates that hull sections can be joined. Porcupine demonstrates that hull can serve purposes other than original design intent. Both examples show that creative engineering and adaptive reuse can extract value from damaged ships written off as total losses. The economic assessment shows both Zubian and Porcupine provided good return on investment. Zubian was created for approximately 30% of new destroyer cost and served 10 years. Porcupine conversion cost approximately 10% of new submarine cost and provided parts and repair services valued at multiple times investment. The return on investment calculations favor adaptive reuse when alternatives are building new ships or accepting reduced operational capability. The strategic value is maintaining force levels when production cannot keep pace with losses. World War I Royal Navy could not replace destroyer losses quickly enough, creating Zubian from damaged ships added one destroyer to fleet at critical time. World War II American submarine force could not get enough replacement parts to forward bases quickly enough, converting Porcupine to depot-provided parts access, reducing operational downtime. Both cases demonstrate that adaptive reuse addresses capability gaps that conventional approaches cannot fill rapidly. The human dimension includes sailors and technicians who made concepts work. The Malta dockyard workers who aligned and joined Zubian's hull sections performed work requiring precision and skill beyond routine repairs. The Porcupine's crew who managed inventory, refurbished components, and fabricated custom parts enabled submarine operations through unglamorous but essential work. The recognition that such contributions matter equally to combat achievements is important for understanding total war effort. The final assessment acknowledges that HMS Zubian and USS Porcupine represent different responses to similar problem. Extracting value from damaged ships. Zubian combines damaged ships to create operational vessel. Porcupine converts damaged ship to support role. Both approaches reflect creative engineering and adaptive thinking. Both succeed in providing capability that would not otherwise exist. The specific approaches differ, but underlying philosophy is same. Damaged ships are not worthless, but are resources that can be reconfigured to meet needs. The mashup destroyer and part shop submarine, separated by war and technology, share commonality in demonstrating that naval vessels are more than single-purpose tools. They are collections of systems, structures, and components that can be recombined and repurposed. The original designs specify particular missions and capabilities, but necessity creates flexibility. The damaged destroyer becomes hybrid destroyer. The failed submarine becomes successful depot. The transformations show that ships, like people, can serve purposes beyond original intent and find value in unexpected roles when circumstances require adaptation. The lesson is that write-offs are premature when creativity and determination can extract utility from damage, that losses can be partially recovered through salvage and repurpose, and that missions can be accomplished through unconventional combinations when conventional approaches fail. HMS Zubian and USS Porcupine, neither famous nor preserved, demonstrate that some of war's most valuable contributions come from making something useful from something broken, creating capability from damage, and refusing to accept that losses cannot be partially recovered through engineering creativity and adaptive reuse.